rational functions, we're talking about functions in which the numerator can be an expression and is divided by a denominator which is also an expression. These can be in the forms of polynomials, of binomials and trinomials, both for the numerator and the denominator. And what ends up happening is we get values, or graphs I should say, with values that approach certain numbers but never actually reach them. When we have graphs that approach certain numbers but never actually reach that number, we call those asymptotes. You can have a vertical asymptote and you can have a horizontal asymptote. Now the trick is, and where people often get confused, is that a vertical asymptote refers to a vertical line that actually cuts through the x-axis, and that's where the graph never actually reaches. So a vertical asymptote has an x value. A horizontal asymptote refers to the horizontal line that actually cuts through a y value, in which the graph also never approaches. So when we talk about the horizontal asymptote, we're actually talking about a y value that the graph never approaches, or never actually reaches, I should say. It approaches but never reaches. Now, vertical asymptotes are the easiest to find because they're just the values that make the denominator equal 0. So let's say I have a quadratic as my function in the denominator. If I factor that quadratic and get the roots, or the zeros, those values are going to be your vertical asymptotes, or the vertical lines that the graph never actually reaches but approaches. Now, to find the horizontal asymptotes of a rational function is significantly more complicated. To help simplify this process, we break rational functions down into 3 categories. The first category would be when the degree of the numerator is equal to the degree of the denominator. When that's the case, the horizontal asymptote is just the ratio between the leading coefficient of the numerator and the leading coefficient of the denominator. And that will present the line, or the value of that would present the line in which the graph never approaches, or the horizontal line. The second category that we can think of when it comes to rational functions is when the numerator has a smaller degree than the denominator. When that occurs, there is a horizontal asymptote at 0. And we're going to demonstrate this a little bit more when it comes to actually solving a problem. The third and final scenario, or type, that we can categorize our rational functions in is when the degree of the numerator is greater than the degree of the denominator. And when that happens, you don't really have a horizontal, or I should say a strictly horizontal asymptote. You have what is called a slant, or an oblique asymptote, which kind of cuts across the graph like an angle. And to find the equation of the oblique asymptote, we have to do something to the numerator. And this itself is kind of a long process. Remember the dividing of polynomials that we were doing prior to exploring rational functions? Yeah. So what you would have to do is you would have to divide the numerator by the denominator, and then the equation that remains as the quotient, that would be the equation of the slant or oblique asymptote. Now the thing is, this only exists if the numerator is 1 degree higher than the denominator. If it's more than that, then this doesn't apply. So let's say we're asked to find all the asymptotes for the following rational function. F at x is equal to 2x plus 5 over x minus 3. When we look at the numerator and the denominator, we can see that they're the same degree. Therefore, we know that our horizontal asymptote is just going to be equal to the ratio of the leading coefficient in the numerator, which is 2x, over the leading coefficient of the denominator, which is x. When we simplify this, that means that we'll have a value of 2. And so that there's a horizontal asymptote at y equals 2. Now, for the vertical asymptote, remember that it's whatever value makes the denominator 0. So we could just take the denominator, x minus 3, set it to 0. So we go x minus 3 equals 0. And then if I isolate for your x, that gives us a value of 3. And so then there's a vertical asymptote at x equals 3. let's say we're asked to find all the asymptotes for this following rational function. Now this is a reciprocal function, and so g at x would be the reciprocal of f at x, which we can assume this to be f at x over here. And so again, we look at the degree of the numerator and the degree of the denominator. We can see that this here has a degree of 0, and then below it has a degree of 2. So that means that since the degree of the numerator is less than the degree of the denominator, there's a horizontal asymptote at y is equal to 0. Now, as for the vertical asymptote, it's whatever makes the denominator 0. So in this case, since we have a quadratic, we're going to factor. So you can factor this either using the quadratic equation or just simple trinomial factoring. So after some good old-fashioned factoring, we got the zeros of the denominator, which means that the vertical asymptotes are at the following, where x is equal to 2, and then x is equal to -1. And what that would mean is this. What these asymptotes mean is that, let's say we were to draw a graph like this. We would have a horizontal asymptote. So I'm gonna write just the horizontal asymptote is going to be what's highlighted in green, and then the vertical asymptotes is going to be what's highlighted in orange. And so we would have a horizontal asymptote at y equals 0, so right around along the 0 line here. And then let's say we actually put our values in. So we've got -1, -2, -3, -4, and then 1, 2, 3, 4. We would have a vertical asymptote at 2. So like this, a straight line that goes through 2. And then another one at -1. And so I'd go over here, 2, -1. And so what that would mean is that our graph cannot cross any of the orange or green lines. It'll approach the orange and green lines, but will never cross the orange and green lines. So let's say we're asked to get the asymptotes for the following function, x squared minus 9 over 2x minus 4. Now, the first thing we do is try to categorize what kind of rational function we're looking at. In this case, we can see that the degree of the numerator is greater than the degree of the denominator. And that means one thing, that we're looking at a slant, or otherwise an oblique asymptote. Not only that, but it's actually greater by exactly 1 degree. So that's more specifically when we have an oblique asymptote. So we could get a vertical asymptote, which is that, whatever makes the denominator equal 0 is the vertical asymptote. So in this case, 2x minus 4, if I isolate, right, set this to 0, and I isolate for your x value here, then I'm going to get an x value of 2. So we've got a vertical asymptote at x equals 2. But this means that there's no strictly horizontal. So what we're going to do is, in this case, we're going to find the equation of the oblique asymptote. And so to get the equation of the oblique asymptote, we're going to divide the numerator by the denominator. And yes, this is going to be through long division. So when we look at the graph here, we can see that there is sort of a slanted region which none of the curves, the red curves, can actually hit. They kind of bend towards a little bit towards the centers here, but this would be known as a slant asymptote, and the equation of this asymptote, right, would be y is equal to 1/2 x plus 1.